Zach, do you want to say some words?
Sure.
Words?
We are all here for Swami's defense. This is one of the best cloud that I've seen. Very, very well.
Thanks for coming.
I guess Swami joined us in 2020. We were just discussing the fact that I can't remember the origin story, and then this was kind of buried in the mists of COVID. And apparently we didn't actually see each other face to face for like a year until we started working together. I guess that's that story. Swami's done a bunch of interesting stuff at the kind of intersection of learning and optimization and control, and has been kind of our resident deep learning guy in the lab. And also, I think, has the distinction of being the person I argue with the most in the lab, which I think is a good thing. So I think that's what I've got to say.
Yeah, so Swami was among the last COVID joiners of the, not quite the last, but among the last COVID of the COVID joiners of the group. So it's been really great. I would also just highlight the thing that's this is a very large audience here. I'm very impressed. You guys are gotta get MLD to be more like this in our everyone coming to visit.
We do have some MLD folks here.
There is MLD folks, that's true, but in general, RI seems to have a nice edge on us right now.
It's popular.
Yeah, or Swami is the real key guy.
Folks, it is amazing.
The thing I would emphasize is just how much sort of the diversity of topics and ideas Swami's brought on and worked on throughout his whole PhD. So I think at times he's worked on things very closely with Zach and I, and at times he's worked on things entirely separate from Zach and I. I think it's actually been, at this point, it's been almost 6 months since we had a joint meeting.
Yeah.
So you guys are, half the time in another lab apparently somewhere on campus. So, but anyway, it's been a real pleasure having Swami around, having sort of someone working on so many things all the time, and I'm really looking forward to seeing what you have for us.
All right. Thank you, folks. The pleasure's all been mine. It has been amazing working with in both the labs and doing all these weird things that you'll hear about. I'll reserve most of those for the acknowledgement section later and finally get started. Thanks everyone for coming. Thanks my committee members for joining. In this talk, we'll be talking about some of the work I've been doing at the intersection of optimization, deep learning, developing some algorithms, architectures for improving optimization layers. I actually got started with deep learning, with optimization back in my undergrad days during an internship where I was trying to work on some visual geometry problems. And before I started it, my mentor was like, you should take an optimization course. I went to YouTube. I tried to look for a course. I found this from Jeff back in 2012. As you might imagine, back in undergrad, for someone who hadn't learned the alphabet, all of this seemed like Shakespeare. And I did not understand much. And by the end of the course and the project, I took away 2 important lessons. One was that optimization is probably not for me. Should probably leave it for bigger brains than mine. And 2, that hardware is also probably not for me. Should probably leave it for folks with more muscle than me. And so I sort of took a little bit of a detour. There was this other thing called deep learning that was cropping up around the time. And turned out all that I needed for that was a little bit of gradient descent. Didn't need to think much about that. A little bit of intuition here and there and a bunch of tuning. And of course, top it up with a little bit of prayer and faith to ensure that things sort of converge at the end of the day. But then, unfortunately, what I did manage to do is stay in robotics. And one thing that you observe if you're working on robotics problems is there are a lot of problems in robotics, whether it's motion planning to localization mapping to inverse problems, sort of have this inherent optimization structure to them. And it just felt wrong to continue or to just ignore the structure and just throw deep networks at people. And as it turns out, as I was grappling with these midlife crises, I saw this paper from Brandon in Zico's group, where they sort of said, yes, there are a lot of these problems where you might have these optimization problems as a structure that you want to impose in your algorithm or method. And what you can do instead is you can just plop them up on top as a layer within a deep network. and differentiate through them, learn the parameters that you need, and you don't need to think as much about the optimization problem itself, and remain the deep learning person you are, and be happy with your lives. And it turns out a lot of applications since then have used optimization layers in various capacities, especially if you look at problems where you sort of know physics incredibly well, for example, problems in geometry, or problems where you sort of need to impose some sort of constraints in the things that you need to spit out. For example, problems in safety in robotics or in power controls for power systems. And as well in problems where you don't have access to as much data. Example in problems in biomedical imaging, robotics, all kinds of areas. And so when I actually came across the paper, I was in an internship at autonomous driving company and working on imitation learning problems. And so I was excited about this. I was like, we should slap an MPC layer on top of our imitation learning policy and see how it works. My mentor at the time was very skeptical. He discouraged me from doing it. I went ahead and did it anyway and could not get anything working. Got a bunch of told you so's at the end. And I was confused. I was not sure why things weren't working. I thought it would be straightforward. And that sort of started a lot of what I ended up doing in my PhD. Essentially trying to figure out what complications we have when we try to add these optimization problems or optimization layers onto deep networks for problems where you sort of can use some of these optimization problems. And some of the problems that you sort of encounter is, to start with, sorry. I'm sorry, we have to start. And so some of the problems that you encounter when you try to add these optimization layers on deep networks would be things like training instabilities. And so the gradients that you get when you differentiate through optimization layers. Sorry.
Are you great?
Yes. Just make sure. I am right. Amazing. Thank you. So, for example, when you try to train networks with an optimization layer on top, you'll see that the gradients are incredibly messed up for various reasons. And even if you do manage to train your models, you'll observe that in a lot of these optimization layers, you bake in a bunch of modeling assumptions about the world, which might often be inaccurate, and as a result, introduce biases in your pipeline. And even if you do manage to mitigate some of the biases, you see that the inference problem is often very slow and almost makes it impractical for real-time usage. And if you do manage to do all that as well, you'll still observe that there are some inherent representational issues arising from the fact that optimization layers are implicit operations, as opposed to regular deep network layers, which are explicit operations. And one of the things that I hope to convey through the thesis as a result is to sort of say that, especially when you try to add these optimization layers onto deep networks, you have to sort of think a little bit deeply about how to plug them in together, resolve some of these issues that arise as a result, and hopefully go through some examples of what that might look like for each of the problems that we just saw. And to start with, I look at the problems in training arising from issues with the gradients that we just discussed. And what we observe specifically is that when you just add on an optimization layer at the end of a network and try to differentiate through it, the gradients that you get from for the network parameters are often high variance. And we'll specifically be looking at this in the context of bundle adjustment layers, which are often found for a lot of geometry problems that in robotics and elsewhere. Ranging from SLAM to structure from motion to 60-pose estimation, so on and so forth. And to take a concrete example, let's say what you do with a bundle adjustment layer is, let's say you have a sequence of frames or a set of frames for an object or a scene. And let's say you have correspondences between those frames to identify the similar patches or similar points across those frames. What you do, what a bundle adjustment layer gives you, is it takes in those correspondences and the frames to spit out the poses for the cameras for each of those frames, as well as a 3D scene that you're observing with those frames. And so this is sort of what it looks like. So you'll have a bunch of frames with correspondences between them. You'll throw those correspondences along with some confidence on how confident you are for each of those correspondences into a bundle adjustment layer. You'll solve an optimization problem, in this case, a weighted least squares problem. And you get the poses for each of the cameras and the 3D scene and the depth for each of those points that you're observing as the output. And the way you get those correspondences and the confidences for those correspondences itself might be with a network that you might have learned. And so you might just be observing a sequence of frames as input. For example, a video, you'll give that as input to a network. The network would then spit out the correspondences as well as the confidence for those correspondences. And then you'll have a bundle adjustment layer at the end to optimize for the poses and depths given those correspondences. And there's this work which sort of said you can sort of have this serial pipeline and differentiate through this entire pipeline to learn the network to solve these kinds of geometry problems. But what you observe is that if you just naively train it, as we just discussed, the training is often very slow and unstable. And especially to give some baseline, to give a sense of what it could be like. This is what you'll see at the end. And if you sort of go a little bit deeper, you'll see that if you plot the signal-to-noise ratios for the gradients as you train your network, the signal-to-noise ratios are actually incredibly low for the naive pipeline we just discussed. Which sort of suggests that the gradient variance here is high. And the question is, why is that the case, right? As it turns out, there are a few different reasons, and I would not bother you with the details. But as it turns out, all of these 3 reasons or multiple reasons fundamentally come from the fact that optimization layers have a bunch of multiplicative and inverse operations that happen within the layer, which result in any variance in the variables getting transferred into variance in the gradients as well. And what that means is the reason it's a little bit harder here as opposed to traditional deep network layers is that with traditional layers, you can sort of add on a normalization layer or a skip connection to sort of mitigate some of the variance, which is not something you can do here because a lot of variables here are grounded in physical quantities and you can just arbitrarily manipulate them. And so the question is, what do we do about them? One of the things that you observe is that a lot of the variance here comes from the fact that there are a lot of outliers. And what I mean here is that when the network is estimating those correspondences, a lot of those correspondences are just plain wrong. And when the correspondences are wrong, it results in a very high variance in the variables for the optimization layers, and both in the input as well as the output, which results in a high variance in the gradients as well. And one of the reasons we, in fact, use the confidences for each of those predictions is to sort of filter out some of those outliers in the input or within the optimization layer itself. And we sort of noticed this and tried a bunch of complicated stuff to mitigate some of these variance issues. But as it turns out, something extremely simple, which is to use the confidences predicted by the network in the input to also just weigh the outliers in the outputs, sort of results in significant benefits and work better than most of the complicated things we tried. And the intuition here fundamentally is that it's often much easier for the network to learn whether a point or whether a correspondence is an outlier instead of learning the correspondence itself. And that sort of results in the network sort of really quickly learning how to weigh the different correspondences instead of learning the accurate mapping between those points. And so if you just make those modifications, it sort of already spoiled the results here, you get much more stable training, much higher signal-to-noise ratio, much lower variance in gradients. And a lot of these modifications are straightforwardly also transfer to a bunch of other settings or geometry problems that we sort of discussed earlier. And what you also observe is like the models that you train as a result also sort of generalize well to other similar in-distribution test sets for these problems. But at the same time, what you do observe is that if you try to test it on an out-of-distribution test set, the performance doesn't change much. And we'll sort of talk, and the reason here is fundamentally that the data you're training on comes from a simulator, and there is some sim to real gap that you just can't do anything about, even if you do manage to train well. We also applied some of these things on some on a problem called loss in space for localizing satellites. And so you just launch a satellite with a camera and an IMU the lost in space problem is where you have a satellite with just a camera and IMU. You have the satellite launched into space. The satellite localizes itself in the orbit to figure out where it is in relative to Earth. What we observed is that we sort of get about 5-ish kilometers of localization accuracy within about 6 hours using just a camera and IMU. And so that concluding the section here, the broad takeaway, I hope, that people take is that when you sort of add these optimization layers and bundle adjustment layers specifically, they often add specific types of operations which result in higher variance. And you have to sort of think carefully about how to mitigate that variance in a lot of these cases. Often involves some prior knowledge about the underlying task itself. But even if you do manage to sort of train well and reduce the variance, you might still often end up at some suboptimal generalization because of the fundamental modeling inaccuracies that sort of exist in your data. And that sort of takes us to the second part of the talk. But before we go there, any questions? All right. And so what we look at here, as we just discussed, is that when you add these optimization layers and when you try to train with these optimization layers, the optimization problem usually involves some assumptions about the world, some modeling assumptions, some models that you might have used for the world. And that results in some modeling inaccuracies when you're trying to deploy a system in the real world. But the question is, can we sort of figure out, or despite those modeling issues, can we still somehow use the model to improve our training? And we'll specifically look at that in the context of policy learning problems, where you might have a real system, such as a quadrotor here, where you'll be trying to learn a controller for the real system. And as you might imagine, the standard way to go about this is to sort of throw a reinforcement learning algorithm at it. You interact with the environment, get some samples, and let's say use a standard reinforcement learning algorithm, such as Q-learning or actor critic or policy gradient algorithms. As you might imagine, this is sort of sample inefficient, especially if you're having to interact with the real world to collect those samples. And especially if you have access to a model or a differentiable model in this case, you might want to use that model somehow in order to accelerate your training, be more sample efficient, so on and so forth. And as it turns out, there's this literature in, sorry, I don't know why the video isn't playing. There's this literature in optimal control called iterative learning control, where you sort of, what you do is you take samples from the real world, but then use the approximate Jacobians from your simulator to speed up your optimization problem, instead of using zeroth order optimization techniques that you typically use with reinforcement learning. And that's actually a demo of one of the early ILC methods, where you just learn a policy on the go within about 30 trials, doing something very similar. The problem with those types of methods is that they're mostly for repeatable problems where you have a very similar task that you're learning. For deterministic use cases, mostly work on policy. You can't really just collect samples and use them post hoc for improving your policy. And it is incredibly problematic when your dynamics is ill-conditioned or discontinuous, because you sort of need to differentiate through your approximate model through long chains in order to update your policy. And so the question we ask is, can you sort of extend some of the fundamental insight to a more general class of reinforcement learning algorithms So that you can sort of get the benefit that you get from using the first order information that you get from an approximate simulator, but be much more general, be amenable to off-policy training, work in stochastic use cases, work with ill-conditioned dynamics, so on and so forth. And we'll probably start with the standard Q learning update that we saw earlier, where we are enforcing consistency on the value function themselves across time steps, based on or using the samples that you collect from the real world. And we introduced this thing called value gradient update, where instead of just enforcing consistency on the value function themselves, you're also now enforcing consistency on the gradient of the value function. And the way you get the way you enforce this constraint is you say that you have your standard Q learning update, differentiate both the LHS and RHS with respect to your initial state action pairs, and enforce consistency of those Jacobians between time steps. And the nice thing here is that now what you can do is if you don't have an accurate model of the world, you can sort of just plop in the Jacobians from the approximate model that you might have to perform those value gradient updates while still evaluating all functions other than the Jacobian itself using real samples. And as you might imagine, or you'd at least hope for this to sort of increase your sample efficiency when using those Jacobians. The nice thing about this update, as we just discussed, is that as opposed to optimal control or like ILC, you get to do this with off-policy algorithms, on-policy algorithms, all kinds of RL algorithms. It's flexible and can work with stochastic problems. You can have a neural net policy or a Q function, do all the approximations you do typically with reinforcement learning. Also, if you have ill-conditioned dynamics, or discontinuous dynamics, you can sort of just skip some of those time steps where you face those ill-conditioning or discontinuities and only enforce these value gradient updates on time steps where you sort of expect some sort of smoothness and continuity. And if you just apply what we just discussed to a bunch of control problems, you observe that you get significant benefits, especially if the problem is somewhat smooth.
Are these people using learned dynamics model or grounded?
This is with ground truth dynamics. We'll come to the. So this is actually just in simulator. And so you have a single sim, you're just learning the policies for the same sim. And so you're just applying the value gradient update along with the Q-learning. And even if your simulator is not differentiable, you can just use a finite difference Jacobian for your sim and get similar benefits. And finally, when you're trying to transfer your policy, let's say from your simulator to a real world or another simulator, which you don't have a model for, you observe that you get similar boosts in performance when trying to use the approximated value gradient update on the target simulator or the target environment. What you also observe, interestingly, is that if you use the value gradient update for training in your original simulator, and then transferred the policy to the real world or to another simulator and fine-tuned it, irrespective of what algorithm you use to do the fine-tuning, the one that you pre-trained with, the value gradient update, ends up transferring better both at initialization as well as after fine-tuning. What this suggests is that the gradient updates sort of inherently give you some bias or some knowledge about the simulator, or give the policy some knowledge about the simulator, which helps it transfer better, regardless of what algorithm you're using for fine-tuning. And I hope the message that came across with that part of the talk is that you'll often have these problems where you might have inaccurate models of the world. The hope is still not lost. You can still use the Jacobians, even if you can't evaluate your policy on using the model themselves, and hope to get some of the benefits that you might get from the first order methods. And that sort of brings us to the third part of the talk, but any questions before that? All right. And one of the things that we discussed earlier is that even if you do manage to train your policy well, even if it does work reasonably well for the tasks that you're looking for, you'll still, for some of those problems, have issues around how slow these optimization layers are. And optimization layers themselves are somewhat slow, but we can often deal with the slowness with some hacks to make sure that we are executing them reasonably fast. But for certain problems, what you'd often need is to sort of loop back the outputs that you get from the optimization layer back to the network, and where the optimization problem itself is a function of, or the network outputs themselves are a function of the optimization methods. And as a result, you have to cycle through these problems multiple times in order to reach convergence of the joint problem. And in doing that, you're sort of having to solve the optimization problem as well as the network inference multiple times, which result in significant slowness. And we'll sort of look at ways in setups like these to try to speed things up a little bit to make these sort of problems feasible to execute online. And we'll specifically be looking at it right now in the context of input optimization problems, where you might have things like latent space optimization for for inverse problems or generative modeling. You might have problems around computing adversarial examples or adversarial training, where you're trying to optimize over the inputs to a network. And likewise, you might have problems around, you might have things like gradient-based meta-learning, where you're trying to optimize over some meta-parameters. It might be inputs to a network in order to quickly adapt to a new task. And concretely looking at the problem itself, you might have an input optimization problem like that, where X here are some inputs that you're trying to optimize. And G theta is your network, parameterized by some parameters theta. And you have a loss function L, which you're trying to minimize minimize for with respect to X. The way you'd go about it in a very standard manner is to sort of perform an inference step with your network at any given input X, and then perform some gradient descent steps on your X in order to perform an update. And repeat the process until the problem converges and you reach an optimal X for the problem L. One of the things that you might notice when you look at the algorithm here is that the X's at consecutive iterations, or the inputs at consecutive iterations, are very similar to each other. And what that means is that the computations that you're doing with your network, or the gradient computations, when you have similar inputs, are likely also very similar. And naively doing the forward and backward passes, as written here, is probably somewhat computationally inefficient. And this will and to make it a little bit more obvious where the inefficiencies come from, we'll replace the network with something called an equilibrium model. And for a little bit of a detour, what we mean by the equilibrium model is, with standard networks, you might have an input X pass through a sequence of layers to get some output. Instead, with an equilibrium model, we have a single layer F, which we're applying iteratively until we reach a convergence on the outputs. And so instead of just passing it through a bunch of layers, you're actually computing a fixed point on your outputs Z, given some input X when you're using an equilibrium model. And so when you try to substitute your network with an equilibrium model, what you see is something like this, where you've essentially replaced all your G thetas with the fixed point constraint that we just saw. And one of the things that you'll observe is that when you replace it with an equilibrium model, you observe that there are these two loops that you're doing for each of those, to compute this minimization problem. One is over the fixed points themselves in your for your equilibrium model. And second is over your gradient descent steps on X. And as you might imagine, the fixed points across the different iterates are likely to be very similar, and sort of makes it very obvious that there is reused or there is non-reused computation that you're doing at each of those iterations or outer iterations. And so the natural thing to do here is say that given that you have these two fixed point iterations looped on top of each other, we might as well just combine them into a single fixed point operation over both your inputs X as well as the outputs Z, and compute a single fixed point iteration jointly. And in some sense, what you're doing here, a little bit more intuitively, is instead of performing an entire fixed point here, you're essentially only performing a single step of the fixed point iteration for each of these iterates. And if you just do something like this, what you observe is that you get about 3 to 4x speedups when performing this joint optimization instead of the looped version that we saw earlier. And in fact, you can sort of put this entire optimization problem as an inner problem for training a network to solve these input optimization problems. And so problems like meta-learning, problems like adversarial training, problems like learning a network to solve inverse problems with these kinds of input optimization processes in the loop.
You were quality. It seems like jointly coupling the fixed point is just like solving a regularized problem in both. So does this bias anything in some way?
So as long as you converge to the optimum,
I'll ask about offline.
right. So, right. So and so if you try to solve if you try to train, one of the things you can do is you can sort of wrap these input optimization problems as part of your inference process and train a network to solve these input optimization problems. We sort of do this for a bunch of different tasks. Again, generative models and inverse problems, we get about similar speedups that we saw with the inference problem itself. For adversarial training, again, we see about 3x speedups, similar to what we saw with the inference problem itself. And again, with meta-learning again, for some simple tasks, we get about 3x speedups when you naively, or when you add these input optimization hacks. And hopefully one of the takeaways here, or the takeaway here from this section is that when you have these looped optimization problems or loop problems where you have to sort of iterate through your network inference as well as the optimization problem, you have a bunch of wasted computation. But given the fact that you're doing very similar computations across iterations, and you'd often want to reuse the computation across those consecutive iterations. And that sort of brings us to the last part of our talk about the representational issues that you face. Any questions before we go there? Awesome. And what we'll be looking at here is representational problems, fundamentally arising from the fact that you have a deep network, which mostly has explicit operations, and an optimization problem, which is essentially an implicit operation, and you're plugging them together without much consideration. And one of the things we'll observe is that if you sort of try to co-design the optimization solver with the network inference step, you'll get much better representational power when you do this. The first problem we look at in this context is in the context of constrained nonlinear programs, specifically in the context of model predictive control, where the optimization layer itself is an MPC or optimal control problem. And so we'll be looking at this in the context of trajectory tracking, where you might have, let's say, a robot giving you observations that you feed to a network, which here might be a policy, which provides some waypoints that your robot needs to follow, which is the theta here. And once you have those waypoints, you might have a tracking controller, which might try to track those waypoints, subject to some dynamics constraints that you might want the waypoints to satisfy, or that you might want the trajectory to satisfy, subject to certain safety constraints that you might want the robot to obey, so on and so forth, in order to make sure that the problem itself, and the MPC problem then spits out the trajectory that you want to execute on the robot. And if you do that naively, we observe a few different representational issues. One is that especially when the optimization solver is iterative and has some nonlinearities in it, single shot estimation of those parameters is a hard problem. And the network itself often does not know how the optimizer is going to respond to the parameters it provides. And moreover, especially for nonlinear problems, you might actually want different parameters for different iterations of the optimization problem. Second, for a lot of these control problems, you might want to warm start the iterates across different iterations, across time steps. And when you try to warm start the optimization iterates across time steps, but the optimization parameters themselves are inferred afresh at each time step, you can imagine that there could be some inconsistency between time steps, which could cause problems. And the third problem is that often when the network is inferring the parameters for the constraints for an optimization problem, it might so happen that the parameters that you infer might actually result in infeasible constraints that you can't even satisfy, even if you do manage to solve your problem well. And a lot of these problems, as you might imagine, happen because the network, when it's predicting the parameters, is fundamentally unaware of the optimizer's state and predicting the parameters in a single shot manner. And so, as we just discussed earlier, instead of just having the network predict the parameters in a single forward pass, you might want to loop through the iterations and say that the network sort of predicts some parameters for the problem, given some observations. The optimizer solves for some trajectories, given those parameters. And then you feed back the trajectories back to the network to refine its estimate of the parameters, and then loop back and forth until you converge on this problem. One of the things that we just discussed earlier is that if you just do this naively, this clearly would be extremely slow and infeasible to deploy on a robot. And given what we just discussed in the inference and efficiency section, we probably want to sort of reuse some of the computation given all of the stuff that we just discussed. The nuance here is that as opposed to earlier, where the inner loop was on the network parameters or the network outputs themselves, the loop here in the inner problem is on the MPC parameters or the MPC problem. Because as opposed to the network being iterative, in this case, the optimization problem is what is iterative. And so the slight modification that we'll make here is we'll again pose it as a joint problem. But then instead of making the network take a single step, we'll have the optimization problem take only a single step of the optimizer and feed back the trajectories to the network for the network to refine the parameters. And so you could, and so in this case, we sort of implement the optimizer as an augmented Lagrangian solver, which takes in some current estimate of the parameters, which might be infeasible, which might be arbitrary, solves a single iteration of the optimization problem to minimize the constraint residuals and the objective, and feeds the trajectories back to the network for the parameters to be updated. But as we saw earlier, what you can also do is you can sort of make the network itself iterative as well, and have the network, as we just discussed earlier, follow an equilibrium model type architecture. And instead of having to solve the network to conversions at each of those iterations, make the inference problem for the equilibrium model iterative as well. And if you make those modifications, you sort of get these two variants for what we call DEC MPC, one with DEC architecture as the network architecture, one with the standard neural net as the network architecture, but then fundamentally in this paradigm of using the solver feedback in order to update the optimizer parameters. And if you sort of compare these two variants of DEC MPC against the corresponding two variants of differentiable MPC, you observe that across a bunch of different environments, we get significant improvements in performance. With the performance between the DEC and the neural net version itself being roughly similar across the instances. But what you do observe, interestingly, is that as you sort of increase the hardness of the problem representationally by making the constraints harder to satisfy, or by reducing the number of warm starting iterations you can perform for each of those time steps, you observe that these the DEC MPC versions get much more, or the gap between the DEC MPC and the differentiable MPC versions improve quite a bit in terms of the downstream performance. This is for a quadrotor pole. So a quadrotor is going from a target to a final position with a pendulum on top with some obstacle avoidance constraints. Likewise, if you sort of try to finally scale the hidden parameters of the network, or the data set size, you observe that a lot of the benefits that you get from TechMPC sort of either get preserved and then sometimes increase as you scale the data set size or the network size. And finally, we perform some hardware experiments where we deploy some of these policies in to control a quad rotor. This is a crazy fly where we assume access to perfect state estimates from a mocap setup, where we are essentially controlling the quad rotor trained on the sim with some virtual obstacles. The obstacles are shown in the sim because we couldn't quite replicate the obstacles in the real world. But the crazy fly here is trying to go from an initial to a target position while avoiding the virtual obstacles imagined in the real world. And by numbers, what we observe is that, again, the DEC MPC versions sort of do somewhat better than the differentiable MPC versions. And the DEC MPC DEC version seems to generalize much better and has fewer collisions or crashes in the process. And so the takeaway, hopefully, here is that especially when you have a complicated solver as part of an optimization loop, you might want to use the solver state as feedback for your network and do some algorithmic tricks in order to ensure that you can sort of co-design the network inference with the solver and get much better representation performance. But there's these other class of problems where you again need some sort of feedback. Specifically, we'll be looking at problems in multi-agent systems where each agent might have access to only partial information, actions, or trust with the users. And we'll be looking at it in the context of mechanism design for LLM agents, where you might have an agentic collective or a market where a bunch of LLM agents are participating, revealing their preferences or predictions, and where the market is reaching some equilibrium, where, as you might imagine, each of those individual participants or agents might only have access to partial information about the equilibrium that you want to attain. And we'll specifically be looking at this in the context of a reputation market, very similar to what you might imagine in something like manifold markets or poly markets, where the agents are trying to predict some quantities which might happen at some point in the future, and are trying to bolster their reputation in the market, in their ability to make accurate predictions. And the market itself is reaching an equilibrium on the estimate for the predictions by pooling all the predictions and the stakes that each of those individual agents make. The representational problems that you might face here are similar to what we just described, but with an added complexity. The first part of it is something that we saw, where the market itself might behave a little bit in unexpected ways, and you might want to take that into account while making predictions with your agent. But on top of that, given that you only have partial information about other agents, there's an added complexity about the hardness of the predictions, given that any prediction or any preferences you might make might be responded to differently from a bunch of the other agents in the market. And so both of these problems in this case make it incredibly hard for the agent or the network to make those single shot predictions that we saw earlier. And the second problem related to warm starting is something that we already discussed, which is that you might want some consistency across time steps, across iterations between the predictions or the preferences that the agent provides. And so specifically, what we'll see is that instead of just having the network expose its predictions or preferences, you might want to reach an iterative equilibrium where the agent sort of gets back the state of the market or the solver for until convergence. Second, instead of having the network or the model directly expose its preferences, you might want to sort of additionally have another optimization solver, which takes in the preferences or predictions from the model and reveals the preferences of predictions in such a way that the resulting state of the market is where the agent would have intended the market to be. And so you'd solve an optimization problem with the solver in the loop, where you'll take the preferences from the model or the predictions from the model and invest and make predictions in the market in order to nudge the state of the market instead of just revealing your preferences of predictions. And third, you might want to do some sort of Bayesian aggregation across time steps in order to ensure that the predictions don't fluctuate wildly between time steps. And if you sort of make these modifications to the agent, you observe that the plot here shows 10 different prediction markets, where we sort of track the reputations for a bunch of different agents in the market, some with all of the scaffolding we discussed, one without the Bayesian averaging, one without the market feedback, one without the optimizer, so on and so forth. And we observe that adding all of the scaffolding results in an agent that vastly outperforms all the other agents across the prediction markets that we ran. And hopefully the conclusion that we get out of this is that it's not just the hardness of the solver itself that needs you to take the feedback from the market, but also the fact that there might be other partially observable entities in the environment, which you might need feedback from in order to refine the actions or predictions that you're making. And that sort of concludes the most of our talk. And we sort of went through the different issues that you might have when you try to add optimization problems or have optimization problems as part of your overall network inference process, from inference inefficiencies to training instabilities, to modeling inaccuracies, to representational issues you might have, and perhaps some solutions or some suggestions that you might want to use when adding those problems as part of your network inference. But then, as I was giving a very similar talk in my proposal, one of the questions that sort of kept bugging me during my proposal was if any of this was actually useful. Does anyone really care about optimization layers? Do people still use them? Should we care? Should you care? And as I sort of described in the early part of the talk, there are a lot of problems which still do end up using optimization layers or optimization problems as part of the inference pipeline. From geometry tasks where you do know the physics reasonably well, to problems in robotic control when you need safety, or in power systems problems where you sort of need to satisfy certain constraints, to problems where you just don't have access to enough data and you want to impose some prior on your architecture in order to learn efficiently. And let me hold the whole thing. So those are sort of the problems that we already see the use of optimization problems in. And hopefully, with some of the problems that I sort of discussed at the end, I've hopefully also given a taste for what optimization layers or what types of problems we might need to use some sort of inner optimization or optimization layers for. One that I already talked about, which is in the context of multi-agent markets or multi-agent collectives, where you might have a lot of agents interacting, and likely the problems like these would only get increasingly important over time. I had a blog recently which sort of goes through a bunch of these problems, bunch of these scenarios where you might have situations like these, even in our current large model era. And the second set of problems, which I've been thinking about recently, which I would have worked on if I had more time in my PhD or was more productive in my PhD, are these problems around meta-learning. I sort of referenced them a little bit in the section around inference inefficiencies for input optimization problem, where we saw that instead of just learning a single model, you might want to learn a model that can adapt quickly to a bunch of downstream tasks. And especially as you have large models, which are specialized and personalized for a bunch of different use cases, how you train those models in order to specialize, fine-tune, or personalized well is an important problem. And in my opinion, would likely be the next scaling law for large models. And that sort of concludes my talk. Hopefully convinced you that optimization layers are useful and are going to remain useful for at least some time until AGI takes over. And that sort of leaves the acknowledgement section. And I don't even know where to start. So it's hard to describe how fortunate I am to have landed in these two labs. People often say lightly that their advisors sort of gave them the freedom and confidence and a bunch of other things to navigate their PhD. But it's hard to overstate how much my advisors have given the freedom, support, and confidence. And like as Zico described in a sugar-coated manner, I sort of ended up working on a completely different problem every year of my PhD. And as you might imagine, when I started any of those problems, I was essentially just throwing stones at the dark. And it requires an incredible degree of patience for my advisors, even for me, to have gone through all that. And that is, I genuinely don't know how to appreciate them enough for having the confidence, for having showing the support that they have throughout those 5 years. Especially in the last part of my year where I still don't know what I'm doing there. And like even individually, I think one of the things I've learned from both of them, I think from Zico, for example, is like the incredible degree of humility that you have, despite being at least 10 orders of magnitude better, smarter, accomplished. And I that is something that I've hoped to learn. And from Zach, I mean, I think there's just a degree of curiosity that I have not seen in people. And I think there is a sense of various points in my PhD where I would sort of get swayed by pressure or by things that are happening around me in the field. And I don't think I could have had a better person to teach me how to stay curious despite all of that. And I am genuinely grateful and thankful for both of them. Granted, a lot of it was through arguments and discussions. And my committee members who have been incredibly supportive. And to just give an instance, when I sort of added them, or when they sort of agreed to be on my committee, I had a meeting with each of them. And to sort of talk about my research, to talk about what I should do. And it's, at least I did not appreciate how much a single interaction can influence and shape what you can do for the next year and a half. And I would say each of those meetings or each of those interactions that I had with each of them in that first meeting shaped significantly how I went about going for the rest of my year and a half. And none of this, of course, could have been possible without a bunch of wonderful collaborators I've had.
It really likes that slide.
I know, I like my lab mates too. A bunch of really wonderful collaborators. And I don't know if I can give a story for each of them, but I will just say that PhD can be a lonely process, especially when you're doing arbitrary things. And having such wonderful collaborators who would sort of tolerate your arbitrariness and randomness, quirks, and still continue to help you, support you through a bunch of, and hopefully me having supported them through a bunch of the projects has been genuinely amazing to have had. And then my lab mates. I'd done some interesting things with them. They've been my lab mates, brainstorming buddies, friends, tour guides, and a whole lot more. And I don't think it's possible to summarize all the things I've done with my lab mates. They've genuinely been one of the most interesting sets of people I've ever met and been with. And I am genuinely surprised how you could have or form a group that has the cohesion and the treats PhD as relationships you form instead of just projects that you work on. And then my roommates. If I had to blame a singular set of people for my lack of productivity, it would I have tried to work. They have not let me. Each evening would be wasted either playing board games, having arbitrary, completely useless discussions, debating pointless topics, and sometimes supporting each other. And like more seriously, they've really been like family that rediscovered every few years. And I'm very lucky to have had these many families to my PhD. And then the RI community itself, as Zico mentioned, it's surprising that RI has these many people showing up to a completely useless defense. Two interpretations there. Either you guys need to be doing more work, or that the community itself is extremely well-knit and extremely supportive. And I'm extremely supportive for everyone in RI who has done amazing things. And then all the friends I've made in Pittsburgh. I don't know where to start and where to end, but again, done a whole bunch of socials with too many people to count. A lot of arbitrary discussions and debates that you might see here. A lot of wasted time. The other set of people I would blame for my lack of productivity. But I definitely could not have done any of what I did without all the time I've spent with these folks and a genuinely amazing crowd. And then my family. They were, to counterbalance all my friends and roommates, they're the set of folks who've tried to keep me productive. Every evening, I would get a call from them. More than my advisors, they would ask me for a report on what I've done, what I finished. I got at least 3 reminders that my defense is at 2 p.m. on and I'm incredibly grateful for all that. I do not know how I could thank any of them, but this is what real privilege looks like. And with that, I would like to thank the committee, thank everyone for being here. Thanks for listening. Questions?
All right, so the process here is that we typically go, actually, I typically violate the process first, I should say. The typical process is the committee asks questions first, but then everyone has to stick around for the whole committee, which I never liked. So I would propose to open it up for audience questions first, and then we'll go to the committee. I do not know why this became the standard to do committees first. felt like we didn't have enough good questions, maybe they'd be taken by the audience, but let's assume we can come up with good questions still and go with the audience first. So any questions first from the group here? Or online, I should add also.
Crickets.
Don't be shy.
Swami, I had a quick question.
Yeah, of course.
So maybe I missed it. Can you describe any sort of properties that the optimization layers need to have for them to fit in this kind of framework? Is there, extensions to this to mixed integer optimization, formulations? What were some of the kind of dirty laundry that you found of which optimization, worked best to support this sort of framework?
All right, thank you. I actually thought all of that was dirty laundry. But what I would say is that I think the general recipe, and I will talk specifically about mixed integer programs as well. The general recipe that I found to be useful to follow is what I sort of described at the very beginning, which is you want to sort of have the optimization problem only for the parts that you absolutely need, and try to learn learn as much of what you need as possible. And so if you can sort of live with a very simple quadratic program, live with that. If you can sort of work with a convex problem where you sort of let your network deal with all the nonlinearities, probably do that. If you can sort of make the network sort of guide the nonlinear program, try to do that. And so the rough takeaway I would say is that like you want to make the life of the optimization problem as easy as possible by learning everything else that you can from the data that you have, and only use the optimization problem if you absolutely need to. And for example, in the case of mixed integer programs, there is some work, for example, from one of the other students from Zico's lab. And you can differentiate through them, learn some mixed integer programs as part of the optimization problem. And it works reasonably well. But even there, I think the way I would go about it in a lot of those cases is have the network sort of deal with most of the inherent non-convexities and non-linearities in the program, and let the optimization problem handle the nice convex portions. Or use a search-based, sampling-based optimization algorithm, which can sort of handle some of those nonlinearities, but then is easy to solve. And the easiness there might be differently defined from how you would define it for a convex problem. But the thing to remember is that you want the optimization problem itself to be easy to solve in some weird, vague notion of easy. Does that answer your question, Mitch?
Yeah, thank you.
Awesome. Yes.
I was curious about the meta learning extension that you hinted to. So specifically, in the second part of your talk, you said basically adding an optimization layer reduces the speed, which is basically the biggest problem behind MAML and things like that. The modification suggests it's like it reduces the time, but I'm curious if we can guarantee that the modification does not change the optimal point that we reach to, or if it does change the optimal point, does it still work because of like generalizability of neural networks?
Yeah, this is sort of very similar to the question that Max was asking during the talk as well. And at least the way I described it, or the modifications I described, doesn't really change the optima itself. So if you had a simple problem where you had a specific optima defined for your original bi-level problem, you would likely reach the same minima. There might be issues around convergence, which is sort of the other part of the problem you were talking about, where if you sort of convert a bi-level program into a joint optimization problem by doing those two update steps in the loop, you often get convergence issues. And what you can, the nice thing about having to learn a network in the process is that it so happens that because you're sort of learning the network or learning your problem to behave well at whatever minima the network reaches as part of the optimization problem, it so happens that you will learn the network to behave well at whatever optima your joint optimization problem reaches. And so especially if you have an overparameterized network, which is sort of a complicated overparameterized network that you're learning, you typically don't have to worry about convergence, as long as you can sort of sacrifice some of, like, as of course, as the problem gets harder, you might need more iterations, but convergence is typically not what you might worry about for the inner optimization problem. There are problems around training the network itself when you have these kinds of non-convex problems, because the gradients that you get from different minima might just conflict and might not take you to the right minima that you might want. And there, you sort of want to go back to what I was describing earlier, which is when you sort of define these optimization problems, you want to define them in a way that it's easy to solve and architect your entire pipeline around the fact that the optimization problem is in some vague manner easy to solve. It could still be nonlinear. You could still be doing meta learning with gradient descent and so on and so forth. And it's a nonlinear problem, but then you might want to parameterize your network in specific ways so that that gradient descent problem or the inner optimization problem is, despite being non-convex, is easy in some way. And so that's probably what it is.
I think we might need to move on to the committee at this point, since
Yes.
we're 45 minutes away from the end. So we do the committee in geographic order. So Vladlen, you're up first.
All right, fun. Okay, I think I'll focus. Yes, I'll focus on the first on the first part of the talk, the differentiable bundle adjustment. So okay, here is a mental model of differentiable bundle adjustment. I'll talk through it a little bit, and then you can correct me and kind of give me your opinion, and we can discuss.
Right.
So bundle adjustment is a nasty, awful, horrible, very bad optimization problem. Because you're basically optimizing correspondence over an image. An image is inherently non-smooth. It is actually one of those classic settings where local minima really do exist, and you can see them. I mean, you can just see them. These are the color changes in an image. As you travel over an image, color gets darker, brighter. It is a very low dimensional space. It is precisely the kind of problem that gives people the intuition that local minima are a very real thing. Turns out that intuition breaks down in higher dimensions. Local minima have a very different character there. But in image space, they really exist, and they're nightmarish. And so you're optimizing correspondences that travel over images, and you keep getting stuck in local minima, and that's bundle adjustment. It's just a nightmare. So of course this will be slow and unstable. And people try to smooth the problem in classic kind of 3D vision. People try to smooth this awful problem using some multi-resolution reasoning. Maybe they start at low resolution, like they literally smooth the problem, right? They smooth the images, start at low resolution, get somewhere, then refine, travel a little bit more, hope they end up in a good place. And there's like 20 or 30 years of suffering to get bundle adjustment to sort of work. Okay, you're trying to do this in a differentiable way. You're trying to backprop through this. And the question is why, right? I mean, that sounds like an awful thing to put yourself through. So there are two options, I guess. So let's talk through both of them. One is, do you learn something in these layers, right? So you're doing deep learning, you're differentiable. Are they parameterized in some way? Do you learn something? Is that the point? Is that why you're doing this? If so, what is it that that you're learning? Or I guess the other case is you're just making classic optimization, the classic bundle adjustment differentiable so that you can backprop through it. Let me pause here and just get your take on learning. Do you want to learn something in those layers? Is that why you're doing this? Or do you just want to backprop through them?
Right. No, I think that's a very good question. I think I feel there's so many questions wrapped in there. And I think I will directly try to answer the last part of the question that you were asking. The objective here is sort of what we described the very beginning, right? Ideally, what you would want to do is have your network just directly learn to predict the poses, directly learn to predict the depths, that if you have supervision on the depths, so on and so forth, instead of having to go through this complicated optimization layer in between. And there's a lot of recent work which tries to do that, right? There's a lot of work which just uses very large data sets, large models to directly go from, let's say, image observations for a few frames and predict the depths or poses or whatever other geometric quantities you want. And the problem there that people observed, and which is one of the reasons why we do this, which is that as you sort of increase the dimensionality of the problem, as you sort of increase the number of frames that you're giving as input, and you want to sort of enforce some sort of consistency between the depths and poses that you're predicting across those time steps, as you sort of increase the depth or the resolution of the images, as you sort of densify the depth maps, as you essentially make the problem harder, and you sort of require more consistency to be maintained across those images or observations that you're getting. It's very hard for deep networks to sort of learn to be extremely accurate with preserving the consistency. And even if you do manage to preserve some semblance of consistency with some learned priors that you might have had, getting metric level, highly accurate depths for downstream tasks, such as in robotics or such as all kinds of other applications, is incredibly hard if you just have a network inferring those quantities. And so it's fundamentally, in my head, a representation problem where the networks just are not, at least that we have right now, are not capable of solving those tasks by themselves. And given that you have a reasonably accurate physical model of the geometry with the bundle adjustment problem, and the problem, as you describe, is mainly with the non-convexity of the problem and how difficult it is to solve the non-convex problem, what you try to do is you try to have a lot of the non-convexity resolved by the network, as we just described earlier, by predicting those confidences, as we alluded to when I was presenting, where what the confidences help you do is resolve some of the non-convexity. And what the confidences say is the network is providing a bunch of these correspondences, which, as it turns out, is a little bit of an easier task than directly predicting depths across the entire scene. And then you have these correspondences, these confidences for each of those correspondences, which helps the problem resolve. This is the rough minima I want to be in because these are the important points that I should optimize for. And that makes the non-convex problem a little bit easier to solve. And that's sort of the overall rationale behind the specific way, at least this pipeline was structured.
Okay. Okay, very good. So next question. So you've made a valiant effort to deal with this gradient variance and the instability induced by these layers. Arguably, the instability, is something that is really tied up with what these layers are, right? So you're backpropping through just a nasty, awful, no good optimization problem So of course it's going to destabilize the rest of the network. You're like spilling out. You're spilling over the awfulness of that optimization problem to the rest of the network by making that thing differentiable. So it's easy to steelman an argument that somehow making bundle adjustment differentiable and sort of allowing it to swing around the rest of the network with its awful high variance and stable gradients is just a bad idea, right? You don't want to do that. You want to contain the awfulness. Have some classic solver just do its thing. Just contain the damage. So in practice, right, not in research papers, but in practice, are you aware of examples where differentiable bundle adjustment layers or something like that was deployed at scale, where it solved some problem in the real world, that people with like a real problem, real systems at scale said, yes, we want to do this. We want to open up, this awful optimization problem and let it affect the rest of the system through backprop.
I think there are two interpretations that I get from practical. I think I am not sure if I know enough about what's going on in specific companies or industries and especially recently, people have gotten much more secretive than they used to be. I'm not quite sure if specific industries are adopting those layers. But what I would say is that I think, especially some of the examples that I showed earlier, where, for example, sorry. Anyway, so for example, the paper or the geometry paper that you see at the very beginning, like here, is still an output from a research lab there, but they're solving extremely complex problems like dynamic scenes, objects are moving, they're using incredibly large data sets to pre-train the early layer of the stack to ensure that the overall problem is reasonably well initialized so that the training problem is nicer. As systems get more complicated, for example, one of the use cases that I show here, like you would want to sort of use all the bag of tricks that you have, which is pre-train as much as possible with the data you have, make the learning problem already close to the minima that you want to reach, so it's easier to work with, and then plop on a bundle adjustment layer or whatever you need to sort of get those extra ounces of performance that you need. And I would imagine that, like, I don't know if industries are using it, but I sure hope they do, given that I genuinely think for a lot of these geometry problems, it is actually useful to use optimization layers or bundle adjustment layers at the end to get those extra ounces of performance from your networks.
Awesome. Very good. Good. To clarify, I think this is amazing, superhuman work. I've done work of this flavor myself, and I have tremendous respect for it. I'm taking kind of the European interpretation of a PhD defense, which is the committee should attack and we should test your ability to defend.
Amazing. Thanks a lot. Amazing questions.
I guess it's distance, right? So
Yeah, so we'll do distance, and now it's a much closer tie, but we'll do max.
Yeah, that was awesome. Really cool, really interesting. I learned a lot from the same proposal. I think actually Zeke and I had a meeting earlier. I'm a big fan of iterative computation as well. I think it's very interesting, but I think I'd like to kind of understand how you disambiguate iterative computation that requires differentiating through a model versus other forms of iterative computation. So we've seen that chain of thought is successful, different people, different opinions as to whether diffusion is about iterative computation. But you could imagine sort of a different setup where rather than solving the fixed point problem by sort of first order optimization, which is what DEQs do, you could imagine trying to solve it through zero order optimization in some way, maybe doing RL for some iterative process or something. why are you, what is your opinion on sort of the relevance of taking gradients through your own network versus other approaches to building iterative computations? So for example, people have tried model predictive control, where you just predict an open loop sequence of actions, you optimize over open loop, and then you do this in a closed loop fashion, right? So now you never need to differentiate through the terrible nastiness of the network. Why is it important that we differentiate through our networks when we want to have greater expressivity?
I wouldn't, so I don't think I think if you're looking for expressivity, I wouldn't care as much about differentiating through any of it. Because like as long as you have computation, you can throw a zeroth order optimizer in there and hope to converge, especially if what you're competing against is gradient descent and first order methods. I do think for a lot of it, you would just be fine with zeroth order optimizers. I do think as the networks get larger and as the problem gets nastier, as the landscape get a little bit more ill-conditioned for the parameters you're learning, it can be a little bit tricky to use zeroth order optimizers. But that's much more problem specific. And I don't think people have tested the limits of zeroth order optimizers.
One follow-up question. So consider a situation where the optimizer variable is much lower dimensional than the number of weights of the number. In this case, one could argue that zero order through this variable might be a lot easier than differentiate the network. But I guess what you're envisioning is a situation where that is a high dimensional parameter, and so
even if it's a low dimensional parameter, it's very much possible that the Jacobian with respect to your output might be conditioned even for the low dimensional quantity. And so as a result, the gradient information that you're getting might still be extremely valuable if the Jacobian is ill-conditioned.
But also conversely, the gradient information can be a lot more stable.
Absolutely. And like that's a trade-off that that's the magic of numerical methods, where you have to sort of figure out where you want to be and what you want to trade off. Do you want the extra ounces of representational power by using the nastiness of the landscape, or do you want to ignore the nastiness of the landscape and make your life easier and use zeroth order methods there? And that's much more of a subjective question on like the specific instances of the problem.
One last question. Currently, when we do things like optimization layers, we're not using things like Atom, right? We're using like actually traditional gradient descent. But one can imagine that sort of what makes optimization work in deep neural networks is not that we can solve arbitrary high-dimensional optimization problems. What works in deep neural networks is, for example, we have Gaussian initialization. This allows for plasticity. We have very highly tuned optimizers. There are other things that are going on. And so my sense is, to what extent do you think that those techniques could be useful for improving the benefits of optimization layers, or in what ways do you think that optimization layers kind of circumvent the pitfalls that we know we needed these other design decisions to
I'm a little bit confused by the question. Like typically, when you're doing gradient descent here, when you're trying to optimize the network parameters, you do compute the gradients as you do with standard deep learning using backprop or using whatever chain rule mechanism you have. And then once you get the gradients, you do whatever you want with the gradients. So you can use Adam, you can use any.
Sure, but my question is, in the works that you've shared, have you been using?
Oh yeah, absolutely. All of them use Adam stochastic optimizers, which use some acceleration. So
Thank you.
thank you.
Yeah.
So Jeff then.
Cool. So I want to pull a little bit on the thread of gradient variance, right? So you introduced that early on with the bundle adjustment problem, where it seemed like it was the most important cause was outliers, places where you mispredicted the correspondence, right? And then there were reinforcement learning problems where variance comes from like big adjustments that you need to make at states that you don't visit very often, right? And then you went through like a sequence of other nasty, horrible optimization problems where, that all want to steal our lunch money. And I guess I'm willing to believe that because there are these really bad optimization problems, that there will be gradient variance. But was there intuition for where it comes from in those? And is there like a general intuition for the next time I come across a new optimization problem, how do I understand the genesis of gradient variance?
Right. I would say I think the sources of gradient variance are not that different. Are very different actually across different instances, but then they're not unique to optimization layers. And the specific ones we saw were because of variable interactions and the transfer of variance from the variables to the gradients. But the genuine issue that you have in a lot of these cases with optimization problems, etc., is that the typical mechanisms that you use to reduce the variance in a lot of these cases that you can sort of do with deep networks, where sort of use normalization layers, use
no longer applicable.
are no longer applicable because the variables that you're using are grounded in real world quantities. And so you can't just arbitrarily manipulate them. You can in some cases, but like in a lot of cases, they are grounded in real quantities. And so it's hard to just arbitrarily manipulate them to mitigate the variance.
So, okay, so you're right. If it starts off bad and you can't have mitigations, that's even worse, right? But for example, the gradient variance in RL is worse than the gradient variance in supervised learning, just because RL is a nastier optimization problem. So it's like there's a source for it as well as the lack of mitigation.
Which is, wait, so are you saying that it's the same in, like RL also has a source for it? Could you
I'm saying that it's not just the lack of the ability to use the mitigations, right? Like there are some training problems just they cause higher gradient variance. And then we have mitigations that might or might not be applicable, but even before that, the variance was higher.
No, absolutely. And I think like, in some sense, I would say like it's similar here, right? Like, I mean, to the RL example you're giving, which is that you do just have these outliers where you have to perform, the additional, as opposed to like, at least in the specific examples you're giving, the issue is more that you get gradients even at those rare examples in RL, and like you have to use the limited gradient you're getting in order to perform your update. And in a lot of these cases where there might be outliers or other weirdnesses, the gradient might just be like incorrect, or like not incorrect, but like bad, and like you don't want to use those gradients, which is sort of what we observed, right? Like you sort of want to eliminate or forget about those gradients. And I don't think the solution there is general. And I think the solution there like comes from the specific source of the problem. And so if the source of the problem, as with RL, is that you're just getting these rare gradients at these rare instances, and you want to be able to judiciously use those gradients, then you would have a very different set of solutions from problems like this, where the gradients or the variance that is coming from those gradients is just as a result of noise, and you want to ignore them. And the solutions as a result would be different.
So that's interesting, right? Because it seems like it's a generic problem that happens across domains, that like every time you're in basically one of these really hard places where you need to use optimization, something crops up and gives you the high variance, right? And it looks like something different in each case. But I have to wonder if there isn't like a common thread that we could find between them.
Yeah, and I think like you did point this out in the proposal as well. And
It's consistent at least.
I don't like, maybe there is. I don't know what that common thread would be. I think just as like I think please go. No. We are brainstorming here. You don't have to.
If you believe networks have a tendency to oversmooth, then relying on their inductive biases alone might take these issues to push yourself. Yeah, that's I don't know. So, yeah.
Right.
Yeah. I mean, it sounds like we're not going to resolve the question today, but that's like, for the next PhD student to answer.
Hopefully. Thank you.
Okay. The other thing I was wondering, you maybe partly answered this already, but so a lot of in the second part of the talk, a lot of the answer to your question was like you had these two different things you wanted to accomplish at once, and you just mash them together into one fixed point computation. And like some fixed points are easier than others, right? Like if you're solving a strictly monotone variational inequality, that's nice. And then if you lose strictness or lose monotonicity, less nice, right? So when you mash them together, do you mess up the quality of the optimization problem? Does it get harder to solve?
Right. And like, I think this goes back to the question Swami was asking,
Right.
which is when you sort of go from the original bi-level formulation, where you're sort of solving the inner problem to convergence, to just using a single iterative of that, or like solving it jointly, you absolutely do lose some guarantees on conversions. You sort of can mess up.
But then the network fixes it, right?
Right.
The
And so
network
the
learns to
nice
fix
thing
it.
that you have here is that you're learning your network in order to do well when at the converged point. And so as long as you've sort of given a little bit thought into how you've designed the optimization problem, how you've sort of designed the variables you're optimizing, you can hope that the network would sort of just
Right.
make your life easier by learning what it needs to learn.
I mean, okay, like how much do I trust that, right? Like,
Which is why the first part of my talk said, if you're doing deep learning, you get ready to
You've had the
have a
faith.
little bit of faith.
how I learned to stop worrying and love the gradient.
You know.
All right. All right, I think that's good. I think
Amazing,
that's
thank
all I
you.
had.
All right, Jack, do you wanna, it's not that common to ask too many questions. but
I'll
wanna
do a
ask
quick
few?
one.
All right.
Maybe I could ask about, I agree with the sort of assertion that like, if we're gonna do this layer stuff, we want to make the optimization problems nice and rely on the network for the non-convex stuff. And so we generally want these to be convex layers, right? QPs, this kind of stuff. So I wanted to connect this though to like some other work that you did in our lab, which is this idea, like the Rayleigh QP idea, that we have this like very nice closed form transformation of any QP you want into like a shallow or weight tighter or DEC, kind of Rayleigh network. So, okay, if every QP is in a very straightforward manner transformable into like a Rayleigh network, like why should I bother with the separate solver?
Because some of those things can be hard to learn. And you might sort of, like for these specific scenarios, right? Like sometimes you might just
Maybe
know.
I'm asking a slightly
Sorry.
different question.
I see.
Which is, okay, if I know that I can turn any QP in a very like turn the crank straightforward way into some network layers, why don't I sort of do that and possibly constrain the weight matrices in such a way that we know that they respond to a convex QP, like some symmetry constraints or whatever. And like now I can, now it's part of a standard training pipeline. I don't have to use an iterative solver and like backprop through implicit function theorem, blah, blah, blah. Like it's just part of the network.
But I feel like you're oversimplifying things a bit there.
It's a
No, I think that's fair. I think even with like expressing Rayleigh QP as a linear layer with some activation function, you end up still solving a fixed point operation. And I don't think, like, let me phrase it differently. As long as you can sort of, and at least the way it registers in my mind is that you are going to have some of these problems which you can express as optimization layers or optimization problems. And instead of expressing those as optimization problems and giving it to an optimization solver, represent this as a different solver, which is represented by a bunch of explicit operations composed of linear and very simple flipping operations, and just solve them like that. And so in my head, the difference is that you are going from one kind of solver to another kind of solver with some additional benefits of perhaps when you express it like that, there are some parameters in the solver or in the way you specified the optimization problem that you might be able to learn or that you might be able to tune by differentiating through the solver. But then, like, fundamentally in my head, it's just a question of whether I'm learning those parameters by keeping them in the formulation of the original optimization problem or transferring them to this transformed space of a bunch of serial explicit operations, and then learning my parameters there in the serial explicit operations. It's very much possible that like learning my parameters in that serialized space gives me representational benefits. And I think it'll probably depend on the specific problem, on where the specific or whether that will give representational benefits. But I don't think there is a general claim I can make in terms of whether operating in that transformed space is the nicer space to be in, even if you're trying to tune some of those parameters.
Okay, cool, thanks. Let's look at that a little bit. I will.
All right, I'll feel bad now. Don't ask one question. Can you go to the deck MPC optimization problem? Maybe just preface my question. How big is that neural network you're talking about there?
Not big. In what, or how do you, or like where is the question coming? Like in what scale are you
I mean,
looking for?
I'm wondering if you can just do direct optimization of the whole thing. Like, why do you need even an iterative method?
Oh, I see. No, yeah, it's definitely not that small.
Okay, but how big? Can you just bring up the slide? It's not showing up.
Oh, it is not. I'm so sorry.
The next one.
Yeah.
Later on, actually. This one, yes. Sure.
Right.
Yeah, how big of a, I mean, and how sparse and everything, what's that network like?
The network would, in this case, I mean, like I think it's like, it's a fully connected network.
Sure, how many hidden units though?
I think I had it here. I think it's probably somewhere around 1024. I think the standard was 1024. Yeah.
But that's plenty to just do Newton's method. I mean, you could just do Newton's method over that whole thing. Like, why not just directly solve that for this as a constraint in an optimization problem and just treat it like a constraint?
I'm not sure if it's worth it, is I think what I would say. Like, I mean, I think we have explored some of this, right? And like much smaller networks than what I have here. If like you have 1024 hidden units, if you have a deck layer, you have 1024 times, let's say with the expansion, like times 5 times 1024. And so you get huge layers with like millions of parameters. And specifying the Hessian there is still a hard problem. And you can probably do it. And like if you really try. But I guess like in my mind, like that is not where the problem is. And so I would not want to spend the effort in fixing it. Gradient descent or like ADAM or quasi-first order methods sort of work reasonably well. And the architectures we have right now are sort of designed for them. And so like maybe like you could do something here to sort of make it work with second order methods, but like I'm not sure if the effort is worth it, even if you could. Is at least my current opinion, but
okay,
happy to change it.
All right. We have 10 minutes left after we adjourn.
Yes.
And then get to have the discussion in the committee.
Awesome. Thank you.
Thanks everyone for coming.